Hello, in this presentation we are going to learn what a decision tree is and how we can implement it. This is our roadmap. First, we do a recall on regression and classification. Next, we learn about decision trees and how they work. Then we are going to implement, visualize, and optimize a decision tree on Python. First of all, let's do a quick recall on what are the regression and classification techniques. There are two types of supervised learning techniques. They are regression and classification. Regression is a process for predicting a continuous value. Look at this dataset. It's related to CO2 emissions of different cars. It includes engine size, cylinders, fuel consumption, and CO2 emission of various models of automobiles. Given this dataset, you can use regression to predict the CO2 emission of a new car by using other fields, such as engine size or number of cylinders. And here I've mentioned some regression algorithms. Among them, we can use regression trees, or more specifically, decision tree regressor. On the other hand, classification is the process of predicting a discrete class label or category. This is the breast cancer Wisconsin dataset. We have 10 features like clump thickness and uniformity of cell size that predict tumor type of patients. These types, which are located in class column, are benign, which means the tumor is non-cancerous, and malignant, which is cancerous. These are some of the algorithms that we can use on a classification problem. As you can see, we can use a decision tree on both regression and classification problems. So, what is a decision tree and how does it work? Decision trees are versatile machine learning algorithms that can perform both classification and regression tasks. They are also the fundamental components of random forests, which are among the most powerful machine learning algorithms available today. A decision tree is a flowchart-like tree structure where the topmost node is known as the root node. An internal node represents a feature or attribute. A branch represents a decision rule, and each leaf node represents the outcome. It learns to partition on the basis of the attribute value. This method is called recursive partitioning. As mentioned, a decision tree consists of the root node, decision or internal node, and leaf or terminal node. The root node is the starting point of the decision tree and can be a simple question like, do you have work to do? And usually create some branches with internal nodes. The non-terminal nodes, which include the root node and other internal node, contain attribute test conditions to separate records that have different characteristics and give yes, no, or true, false answers. In this simple example, we start by asking a question. If you have work to do, you should stay in and finish your task. If you don't have work, we can ask another question, like the weather condition. If it's sunny, you can go to the beach, and if it's rainy and your friends are free, you can go to movies. So how does a decision tree work on a scatter plot? The splits are done in such way to maximize the number of points in a certain category. Each split tries to minimize entropy, which I'll cover later. The first split happens at x2 equals to 60. So the data is divided into two segments, x2 less than 60 and x2 greater than 60. We'll call it split 1. The second split happens at x1 equal to 50. But it only happens to the data points where x2 is greater than 60. And it goes on recursively, so you can see that all the terminal leaves represent a category, either red or green. Let's get a bit deeper into how a decision tree works. The basic idea behind any decision tree algorithm is as follows. In step 1, the decision tree selects the best attribute using attribute selection measures, or ASM, to split the records. In step 2, the algorithm makes that attribute a decision node and breaks the dataset into smaller subsets. In step 3, it starts tree building by repeating this process recursively for each child until one of these conditions is achieved. All the tuples belong to the same attribute value, or there are no more remaining attributes, or there are no more instances. Attribute selection measure is a heuristic for selecting the splitting criterion that partitions the data in the best possible manner. It is also known as splitting rules because it helps us to determine breakpoints for tuples on a given node. ASM provides a rank to each feature or attribute by explaining the given dataset. The best scored attribute will be selected as a splitting attribute. The information gain is one of the most popular selection measures, which I'll cover later. So, how does a decision tree select the attribute using recursive partitioning on a dataset? Let's assume that we have a dataset of 14 patients with high cholesterol and we want to provide better drug effectiveness for the 15th patients using decision trees. Here we have 6 columns: patient ID, age, sex, blood pressure, cholesterol, and the type of the drug. In this dataset, 5 patients are using drug A and 9 patients are using drug B. The algorithm chooses the most predictive feature to split the data on. Let's say we pick cholesterol as the first attribute to split the data. This will split our data into 2 branches. As you can see, if the patient has high cholesterol, we cannot say with high enough confidence that drug B might be suitable for him, because there are still 3 other patients that take drug A. It is an example of bad attribute selection for splitting the data. So let's try another attribute. Again, we have our 14 cases. This time, we pick the sex attribute of patients. It will split our data into 2 branches, male and female. As you can see, if the patient is female, we can say drug B might be suitable for her with high certainty. But if the patient is male, we don't have sufficient evidence or information to determine if drug A or drug B is suitable. However, it is still a better choice in comparison with the cholesterol attribute, because the results in the nodes are more pure. It means nodes that are either mostly drug A or drug B. So we can say the sex attribute is more significant than cholesterol, or in other words, it's more predictive than the other attributes. Indeed, predictiveness is based on a decrease in the impurity of nodes. We are looking for the best feature to decrease the impurity of patients in the leaves, after splitting them up based on that feature. If we go one step further on the male patient branch, we again test other attributes to split the subtree. We test cholesterol again here. As you can see, it results in even more pure leaves. A node in the tree is considered pure if 100% of the cases the nodes fall into a specific category of the target field. In fact, the method uses recursive partitioning to split the training records into segments by minimizing the impurity at each step. Impurity of nodes is calculated by the entropy of data in the node. So, what is entropy? Entropy is the amount of information disorder, or the amount of randomness in the data. The entropy in the node depends on how much random data is in that node, and is calculated for each node. If the samples are completely homogeneous, the entropy is 0, and if the samples are equally divided, it has an entropy of 1. This means if all the data in a node are either drug A or drug B, then the entropy is 0. But if half of the data are drug A and the other half are B, then the entropy is 1. You can easily calculate the entropy of a node using the frequency table of the attribute through the entropy formula, where P is for the proportion or ratio of a category such as drug A or drug B. As an example, let's calculate the entropy of the dataset before splitting it. We have 9 occurrences of drug B and 5 for drug A. You can embed these numbers into the entropy formula to calculate the impurity of the target attribute before splitting it. In this case, it is 0.94. Now we can test different attributes to find the one with the most predictiveness, which results in 2 more pure branches. We should go through all the attributes and calculate the entropy after the split, and then choose the best attribute. Let's first select the cholesterol of the patient and see how the data gets split based on its values. For example, when it is normal, we have 6 for drug B and 2 for drug A. We can calculate the entropy of this node based on the distribution of drug A and drug B, which is 0.8 in this case. But when cholesterol is high, the data is split into 3 for drug B and 3 for drug A. Calculating its entropy, we can see it would be 1, so it wouldn't be a good attribute to select. Now let's check another attribute. As you can see, when we use the sex attribute to split the data, when its value is female, we have 3 patients that responded to drug B and 4 patients that responded to drug A. The entropy for this node is 0.98, which is not very promising. However, on other side of the branch, when the value of the sex attribute is male, the result is more pure with 6 for drug B and only 1 for drug A. The entropy for this group is 0.59. Now the question is, between the cholesterol and sex attribute, which one is a better choice? Or, in other words, which attribute results in more pure nodes for our drugs? The answer is the tree with the higher information gain after splitting. So what is information gain? Information gain is the information that can increase the level of certainty after splitting. It is the entropy of a tree before the split minus the weighted entropy after the split by an attribute. As entropy or amount of randomness decreases, the information gain or amount of certainty increases. and vice versa. Let's see how information gain is calculated for the sex attribute. As mentioned, the information gain is the entropy of the tree before the split minus the weighted entropy after the split. If we use the sex attribute to split the dataset after calculation, the information gain of the tree is 0.151. We can calculate the information gain of the tree if we use cholesterol as well. It is 0.48. Now the question is, which attribute is more suitable? Well, as mentioned, the tree with the higher information gain after splitting. This means the sex attribute. After selecting sex attribute, we should repeat the process for each branch and test each of the other attributes to reach the most pure leaves. Now I want to talk about one more definition in decision trees. The Gini index, which is used by the classification and regression tree, or CART for short, which is a term introduced by Leo Brayman to refer to decision tree algorithms that can be used for classification or regression. CART algorithm is a greedy algorithm. It greedily searches for an optimum speed at the top level, then repeats the process at each level. A greedy algorithm often produces a reasonably good solution, but it's not guaranteed to be the optimal solution. The representation for the CART model is a simple binary tree, and the Gini impurity can be calculated by this formula, where Px is the proportion of the samples that belongs to the class X for particular node. Here we have a decision node that has 20 samples as students, which half of them are playing cricket. Now it branches into two impure nodes, and by calculating the probability of students who play cricket and who are not playing, we can calculate the Gini index. Gini ranges from 0 to 0.5, and the higher this value, the more pure the nodes will be. The attribute with a minimum Gini index is chosen as the splitting attribute. There is one more thing. Despite the power of decision trees, they can easily result in overfitting of the training data. One of the most common problems when training a decision tree is to learn the optimal size of the resulting tree that leads to better accuracy of the model. A tree that has too many branches and layers can result in overfitting the training data. Pruning a decision tree helps to prevent overfitting the training data so that our model generalizes well to unseen data. Pruning a decision tree means removing a subtree that is redundant and not a useful split and replacing it with a leaf node. Decision tree pruning can be divided into two types, pre-pruning and post-pruning. Pre-pruning, also known as early stopping rule, is the method where the subtree construction is halted at a particular node after evaluation of some measure. These measures can be the Gini impurity or the information gain. In other words, pre-pruning overcomes the overfitting by decreasing the decision tree depth. As we are going to use the Scikit-learn library, and because it only has a built-in function for pre-pruning, I've only covered the pre-pruning here. Okay, by now we have learned the main concepts behind the decision tree algorithm. In this slide, you can see some use cases of decision trees. Decision trees have many use cases, from search engine optimization used by companies like Google to pedestrian detection cameras used in automated driving cars. It can also be combined with face recognition systems for surveillance. Decision tree also is used by Microsoft Kinect to detect which part of the body is moving. Though they actually use more complex models like a random forest. But the idea and algorithm behind it is the same as a decision tree. And as the last subject of this video, I want to talk about some pros and cons of the decision tree model. The advantages are: decision tree is easy to interpret and visualize. It requires fewer data preprocessing, which means missing values do not affect the model, and also we do not need to normalize or scale the data. As we saw, it can be used for both regression and classification problems. It can be used for feature engineering, such as predicting missing values, suitable for variable selection. The disadvantages are, as we saw on slide 19, decision trees are more prone to overfitting. The small change in data can result in a different decision tree, though this can be reduced by bagging and boosting algorithms. In comparison to other algorithms, decision trees have higher time complexity. The decision tree algorithm is inadequate for applying regression and predicting continuous values. You can read more about the other pros and cons and how you can improve them on your own. We are done here. I've included the sources I've used for this presentation. Thanks for your attention, and now we are going to implement a decision tree with Python. Now it's time for coding. We are going to implement a simple decision tree that classifies the gestational diabetes, which means high blood glucose during pregnancy. We will use the Pima Indian diabetes dataset. I will use Google Colab environment as it has all the necessary libraries we need. But you can use your favorite IDE. Note that if you are using any environment rather than Colab, you should first install the necessary libraries. You can access my Colab notebook from this URL. I will use a single pip install command pip install command and write package names separated by a single space. Pandas Scikit-learn 6 graph with pi.plus. As you can see, all the necessary libraries are installed. Now we are going to import the libraries so we can use them. Import pandas as PD. It allows us to use the CSV data frame from Scikit-learn.tree import DecisionTreeClassifier, which is the decision tree classifier from the Scikit-learn library. From Scikit-learn model selection import train test split. We will use it to train our model. From Scikit-learn import metrics. It allows us to calculate the accuracy. from Scikit-learn dot tree import export graph please. This will export the decision tree as a dot file from 6 import string io. To use the dot file from ipython dot display import image displays the tree as dot file. Import hi.plus, which converts the dot file to PNG. Now we will run this using Control Enter and Control MB for a new code cell. And we will download the dataset using the wget command. It will save the dataset file with the name pima.csv. wget o pima.csv. I've created a short link so you can easily download the dataset. https://bit.ly/pima-idd. Okay, now we can load and preview the data. Pima equals pd.read csv pima.csv pima.head, which will load the first 5 rows. Let's see how many diabetic patients we have. I will make it look a little better using emojis. Print non-diabetic Pima outcome equals 0.sum, and I will copy paste this. As you can see, we have 500 non-diabetic patients and 268 diabetic patients. Now we need to divide the given columns into 2 types of variables: dependent or target variable and independent variable or feature variables. So we take all columns except the last one, which is the outcome that we want to use as target variable, and store its data frame in the variable x. Feature calls equals pima.columns dot values dot to list x equals Pima feature calls. And we select the outcome column as target variable. Y equals Pima dot outcome. Let's print and see our variables. I used fstring here to print a little prettier. Print fstring x \n, which will create a new line. Multiplied by 10 and \n y variable. As you can see, I've added all the columns except the outcome in x variable and added the outcome in y variable. Now we should split the data. To understand model performance, dividing the data set into a training set and a test set is a good strategy. Let's split the data set by using the Scikit-learn function train test split. We need to pass 3 parameters: features, target, and test set size. X underline train, X underline test, Y underline train, and Y underline test equals train test split X, Y, test size equal 0.3. Test size will be 0.3, which is 30% of our data. Approximately 230 rows will be used as test data. Random state equals 40. And random state ensures that the split of our data will be the same on each run. It can be any integer number. Now we are going to create our decision tree. To do this, first we will fit the X and Y train data using DecisionTreeClassifier and store it in the variable CLF. CLF equals DecisionTreeClassifier. Remember that the DecisionTreeClassifier is a function, so you should put a closing parenthesis after calling. Dot fit X underline train and Y underline train. Then we will predict the X test based on the CLF variable, which contains our training model. Y pred equals CLF dot predict X underline test. Now let's estimate how accurately our model can predict the test data. Accuracy can be computed by comparing actual test values and predicted values. Print accuracy matrix dot accuracy score y underline test and y underline predict. Well, we have got a classification rate of approximately 70%, considered as a good accuracy. We can improve it by tuning the parameters, which we'll do after visualization. As we have installed and imported the libraries at the beginning, here we will just call the functions. Dot underline data equals string IO. String IO allows file-like access to a string so we can visualize the decision tree. Export graph with CLF out underline file equals dot data. CLF takes decision tree and out file will be the dot data so it can be viewed as image. Special characters equal true. A special character set to true for PostScript compatibility. Feature names equal feature underline calls. Feature names will be our column names. And class underline names equal list of n as no and y as yes. Name of target classes in ascending order, which identifies the patient if the patient is diabetic or not. Graph equals pi dot plus dot graph from dot data dot get value. This gets the value of dot data and converts it to graph. And we will write the graph as PNG file, graph dot write PNG diabetes dot PNG. And we will use the image function that we previously imported from ipython.display library to create the PNG file. Image graph dot create PNG. I have a typo here. Oh, I have missed two parameters here. Fillet equals true and rounded equals true. Fillet shows majority class of classification, and rounded draws boxes with rounded corners. Now I rerun this. As you can see, this results in a huge decision tree that is hard to read. In other words, it's an unpruned decision tree. In the decision tree chart, each internal node has a decision rule that splits the data. Gini is referred to as the Gini ratio, which measures the impurity of the node. You can say a node is pure when all of its records belong to the same class. This unpruned decision tree is not easy to understand, so we will work on pruning and optimization of the decision tree. To start optimization, I will copy and paste the above cells from here. Now we will add 3 parameters to decision tree classifier. Criterion equals Gini. This allows us to change the attribute selection measure. It can be entropy for information gain or Gini for gene index. I will use the default value Gini as it provides better accuracy because it reduces false classification. Max depth equals 3. The maximum depth can be used to prune the decision tree. Higher values of maximum depth can cause overfitting and lower values cause underfitting. Splitter equals random. This parameter allows us to choose the split strategy. Supported options are best and random. The random setting selects a feature at random, then splits it at random and calculates the Gini. It repeats this a number of times, comparing all the splits and then asking the best one. It's less computation intensive than the best setting, which calculates the optimal split of every feature at every leaf. It's also less prone to overfitting. Now I will rerun this using Ctrl-Enter. As you can see, we have got an accuracy of 0.71, which is 1% better from the previous one. As you can see, this pruned model is less complex, easier to understand, and explainable compared to the previous decision tree model. At the root, we have 537 samples. If the BMI less than or equal to 27, the condition will be true and the algorithm continues to the left path of the decision tree. As the tree goes deeper, there are more conditions like the first one. Each results in a true-false statement. Usually as we go deeper, the gene index will decrease. It indicates that the leaves are becoming more pure and our prediction should be more accurate. For example, consider this node. we have Gini index of 0.03 and the node has 66 samples. 65 samples on category 0 and 1 sample on category 1. Category 0 is non-diabetic and category 1 is diabetic. As most of our samples are non-diabetic, the decision tree algorithm correctly predicted the patient's class as N, which is non-diabetic. Also, we can know how the decision tree works on our trained data by looking at the color of the nodes. The lower the Gini index or entropy, the darker the color of the node. For example, an orange node indicates that the patient is most likely non-diabetic, and a blue node indicates that the patient most likely belongs to the class Y or is diabetic. The white nodes have the least amount of certainty. Thanks for listening, and I hope you enjoyed this video. Goodbye.